Hello, so if you remember, in the last video, we were talking through this idea of measures of central tendency, weren't we? I know we were talking about other things as well, but measures of central tendency was the main one. And what that literally said was find me one value that best represents my data set. So if I have a data set in front of me, can you just give me one value that would represent that data set there? For example, if I had the heights of people in my class and I just wanted to find out my average height, okay, one value that just represents all the heights of the people in my class, that would be a measure of central tendency. And if you remember, there were three. There was the mean, there was the median, and then there was the mode. They are all averages, okay? And by definition, a measure of central tendency simply says, where does the center of my data tend towards? Now, there are some instances where actually a measure of central tendency is okay, but it's not enough on its own. I need to understand something a little bit more about what's happening with my data, okay? And this is where measures of variation comes in. Another word for this is a measure of spread. So let me show you a real life example of a data set, okay? So this is true real life data of 13 children's hospitals in the UK. And it basically looks at the survival rates of these children's hospitals after heart surgery. So in other words, if a child goes in for heart surgery, 30 days later, is that child still alive? And the survival rate would just simply be the number of people that are still alive divided by the total number of operations that have taken place. So here I've basically got a bar chart. Now notice I'm doing the bar chart horizontally, that's fine, okay, you don't have to do it vertically all the time. But each bar basically represents a different hospital, and you can see the names of the hospitals on the left-hand side, and obviously along the x-axis is the survival rate. So clearly the length of the bar represents the survival rate. The longer the bar, the higher the survival rate, okay, which means that more people had survived. So if I ask the question now, if you had to have heart surgery, which hospital would you go to? You'd be like, well, I can see which hospital I definitely won't be going to, the bottom one, okay, because that bar is really, really short, London Harley Street. That bar is really, really short, which means it has a lower survival rate relative to the others, which means that fewer people had survived. Whereas if you look at London Great Ormond Street, which had a much longer bar, that means that more people had survived. But now let me show you exactly the same data. So I've not changed anything about the data, I've just changed one small little thing about the plot. Now if I ask you the same question, which hospital would you go to? You're probably like, well actually there's not much difference between them, right? So actually any of them would be fine, okay? So what have I changed between this plot and this plot? Well, this plot here, the one on your screen, if you look at the x-axis, I've changed the range of the survival rates. Okay, so the survival rates start at the true value, which is 0. That means that nobody survived, right the way up to the maximum value the survival rate could have, which is 100%. That means everybody had survived. Whereas on the other graph, I'd kind of only shown the survival rates between 95.5% and a 99.5% range. So that's one thing to watch out for when you're plotting, okay? And certainly as a statistician, that's one thing you should watch out for. This graph gives the illusion that there is a massive difference between the hospitals, okay? This hospital is performing much worse than the hospital up here, for example. Whereas this one shows what's actually probably happening, which is that there's not much difference between these hospitals, okay? So what I need is a measure which means that I won't fall into this same trap again. So I need to talk about the spread of the data. Spread is just simply what's the differences between the data doing, okay? So let's show you the data again, but let me show you it in a table format. So in the first column, you can see I've got the different hospitals, and each row represents a different hospital. And I'm interested in that last row here, last column, sorry, here, which is the survival rate, okay? So what I could do to understand the differences between the survival rates of the hospitals is look at the range. Now the range is simply the differences in the extreme values. So the extreme values, I simply mean, find me the highest survival rate. So here it is, London Great Ormond Street at 99.2. That's the highest survival rate in all of my data, okay? And then find me the lowest survival rate in my data, which is London Harley Street. So 95.9% is the lowest survival rate in my data. So to find the range, what I would need to do is just simply find the difference between these two values. In other words, take 99.2% and take away 95.9%. And that gives me a range down here of 3.3%. Okay? So one measure of spread is a range. It's just simply what is the difference in the extreme values. Now actually, we've already come across another type of range, okay? Another type of spread. It's when we're dealing with box plots, okay? Because if you remember, a box plot simply says split the data up into 4 equal parts. So basically each data point, so each part, there's the same number of data points in. So if I show you with the first data set, if I split the data in half, then basically there's the same number of data points down here as up here. And then I'm going to split the data points in half again. So basically now I've got 4 parts, so I split the data into 4 parts, and in each part I've got the same number of data points, okay? And you can see that all I'm basically asking now is how spread out are these split points, okay? And one easy way of doing that is actually plotting these split points, okay? And we call that a box plot. We've seen that before, okay? Whereas if I look at the next data set, well, there's my midpoint, and I split those in half again, so I get my 4 parts, my quartiles, which are the points where I'm splitting the data. You can see that on the box plot now, these data points, these split points, are much further spread out, okay? So one measure of spread, we've done it before, is with quartiles. It simply says when you split the data into 4 equal parts, how spread out are these quartiles? If they're really spread out, you can see that on the box plot, it means that the data is more spread out as well. Okay, whereas if they're more closely clustered together, it means that that data has a lower spread, right? So basically we have a couple of different measures of spread already on our bags. We've got range, just looks at that, the difference between the highest and the lowest value. And we've also got quartiles. Now, I've also put some more here. Deciles is if you want to split the data up into 10 equal parts. And percentiles if you want to split the data up into 100 equal parts, okay? So you've got quartiles, which splits the data up into 4 equal parts. Deciles splits the data up into 10 equal parts. And percentiles splits the data up into 100 equal parts, okay? But there's a couple of issues with each of these measures of spread. Let me work with these ones first of all, okay? So the quartiles, the deciles and percentiles, where you're splitting the data up into equal chunks and then seeing how far apart those split points are. The issue with each of these is there's more than one value, right? If I go back to my measure of central tendency, okay, so my averages, my measure of central tendency, that is just simply one value, right? That's just simply one value. Whereas if you look here with quartiles, deciles, percentiles, that's more than one value, right? Which is not really what I want. The nice thing about an average is that it's just one value that I need to worry about in general. Whereas if I'm looking at quartiles, deciles, percentiles, these are measures of spread, which is more what I want to get to. I want to understand how spread out is the data. But the issue with these is there's more than one value. Now, range is good because that is just one value. But if I go back to my hospitals example, and if I change London Harley Street now, not to be 95.9% survival rate, but maybe to be a 50% survival rate, okay, then suddenly I would call this an outlier. Because actually if you look at the rest of the hospital survival rates, they're quite closely clustered together. But if I have London Harley Street now, not as 95.9%, but as 50%, then suddenly my range is going to be made massive just because of that one outlier. And I don't really want to sort of worry about that. If the range is so heavily influenced by outliers, then I don't really want to worry about that. It goes from 3.3%, if this was 50%, it goes from 3.3% down to 49.2%, okay? So the range is really heavily influenced by outliers. So I want really another measure, okay? So quartiles, deciles, percentiles, okay, but they're more than one value that I've got to work with. Range is fine, it's just one value, however it's really heavily influenced by outliers. So what I want to do is just come up with one value that I need to worry about to get a decent measure of the spread of my data. So let me plot this data again, okay, but let me plot it more like a scatter graph. So basically along the x-axis I've got the hospital, along the y-axis I've got the survival rates, and I've just basically plotted them as points rather than as bars, okay. So one thing that I could do is look at the average survival rate. Why not? Okay, so I basically take each of these survival rates, I add them together, and then I divide by the 13 hospitals that I've got to get an average survival rate of about there. And you can see that I put the average survival rate in as a horizontal line across here, and it's about 98%. It's a little bit less than 98%, but it's about 98% for our purposes. All right. Now, if I looked at this data, and if I wasn't a trained statistician, perhaps if I looked at it naively, then I might be led to believe, well, look at these hospitals in blue. All these hospitals in blue have a survival rate which is above the average line. Okay, so if you're above the average line, it means you're doing well. It means you're above average. You've got more people that are surviving than what you expect. Whereas if you're in red, it means that you're below average, which means you've got more people dying than what you expect. You're below the average. All right. So all these hospitals are above average and all these hospitals are below average. So if you think about average as expectations, then it means that the ones coloured in red have more deaths than what you expect, because average is just simply an expectation. But is this a fair conclusion to make? Well, I would argue no. And the reason being is because an average is just a measure of central tendency. We've done this before. In other words, it's where is the centre of your data tending towards. So by definition, because it's a measure of central tendency, then 50% of your data should be above average and 50% of your data should be below average anyway, just by pure chance, okay? Just really luck of the draw about where you end up. Do you end up above average or do you end up below average? Okay, and it's just pure chance. So actually to say that all these hospitals in red have more deaths than expected, technically it's correct, but it's not a very fair statement to make. Okay, because actually it's expected that half of the hospitals should be below average anyway. So what I want to do is incorporate this in my measure of spread, okay? So I want to look at the average distance from the mean and then say, are you above the average distance from the mean? So not whether are you above average or below average, so simply just above or below this line. I want to say, are you above the average distance from the line? Then you can start to make a more meaningful comparison, okay? So let's have a look at this. So what I want to do is I want to measure the distance. Now, first things first, I'm just going to number each of these hospitals. So each of these data points represents a different hospital. I'm just going to number them. So this here would be hospital 1, which I'm just going to call X1. So rather than saying hospital 1 all the time, I'm just going to say X1, and this would be hospital 2, hospital 3, hospital 4, etc., etc. Okay? So if I want to measure the distances, okay, which is just simply the distance between the hospital survival rate and the expected survival rate, so in other words the average, okay, what I'm going to do is just simply take those two things away from each other. Take the survival rate and the average survival rate and just take them away from each other, and I'll basically get a distance. Okay, so if I do that, I get these numbers here. Now if you look here, you've got some values which are positive and some values are negative. And I wonder if you can think, why are some values positive and some values negative? Well, the reason is simply because of how we calculated our distances. We took the survival rate first and then took away the average survival rate. Okay, so if you were above average, that's fine because you've got a bigger number. For example, this one here is about 99.25%, and you're taking away the average, which is 98%. In other words, you're taking away a smaller number. So if you start with a bigger number and you take away a smaller number, it means that the final number should be positive. So all the ones above the line, above the average line, will all be positive. But obviously the poor souls which are below the average line, for example, this one here at about 95.7-ish, because you're below average, that's less than the average value, which means that you're going to end up with a negative value when you take the survival rate and take away the average itself. Okay, so clearly what we want to do here is find the average distance from the mean. Okay, so if you look at all of these distances, you want to ask yourself the question, what is the average distance? How far are you expected to be away from the mean line? Okay, and we give this a special name. We call it the standard deviation. So deviation is a bit like variation. Okay, it's how much you deviate. And standard is how much you expected to. Okay, so the average distance from the mean, it's really important. Average distance from the mean is given a special name. It's called the standard deviation. So here we've got all our distances here on the left-hand side. Okay, so here are all the distances which we just calculated for each hospital. Okay, now if I want to find the average, surely I should just add all of these values together and divide by the number of hospitals which I've got. That's how you calculate an average, right? Add all your values together, divide by the number of values which you've got. Well, actually in this case, that's not appropriate. And the reason being is because look, you've got some distances which are positive, but some distances which are negative. So basically, if you add together all of these values, there will be some values which cancel each other out. For example, have a look at hospital 2 and hospital 4. Hospital 2 was 0.1 away from the mean in the positive direction, in other words above average, but hospital 4 was still 0.1% away from the average, but it was below average, so it was in the negative direction. Okay? So if I add them together, it means that 0.1 plus negative 0.1 will just result in 0. That's not what I want. Okay? So what I need to do is try and make all of these values positive. Okay? So let's just think, how could I make all of these values positive? Well, one way is by multiplying through by -1, okay? So basically, whenever I see a positive value, okay, I can just leave it alone. But if I see a negative value, I can say, right, make that positive by multiplying by -1. So you basically just go through each hospital and say, right, that's negative, multiply by -1. That's positive, leave it alone. That's positive, leave it alone. That's negative, multiply by -1. That's positive, leave it alone. That's positive, leave it alone, and etc, etc. You just simply do a decision tree. If it's positive, leave it alone. If it's negative, multiply by -1. Issue is, however, this will take a lot of time. So what I really want is an operation which I can apply to all of my values, and they'll always end up positive regardless of whether they were positive or negative to begin with. Well, fortunately, there's one really easy way of doing that. Okay? Hopefully you can think of an operation which makes everything positive, and it's squaring. So if I take my distance, okay, and then if I square it, that will always be positive. Okay, so for example, if I start with a distance of 2, if I square that, that will become 4. Okay, but the issue is, okay, I don't want 4, do I? I want to get back to what 2 was. Okay, so in order to get back again, I just undo the squaring, which is square rooting. Okay, so now if I square root this, this comes back as 2. Okay, so you can see here that if I start with 2, and if I follow the process of squaring and then immediately square rooting, I always end up with a positive value. Let's just check it with a negative value. Let's check it with, for example, -3. Okay, so if I square it first of all, -3 squared is 9, but then if I square root it, I'm back at 3 again. Okay, so that's good because I've gone from a -3 to a +3. So you notice this process of squaring something but then immediately square rooting it doesn't actually matter whether it was positive or negative to begin with. It will always end up as being positive. Okay, so this is what I want to do. In order to make a value positive, I'm just going to square it and then immediately square root it. Okay, so in order to find the average distance, first things first, I need to square all of those values. Then I'm going to divide them by the number which I've got, and then I'm going to square root them. Okay, so here we go. Let's just deal with this then. Well, have a look. You notice that I've got all of the squares of the distances added together. Okay, well, instead of saying all of the squares of the distances added together, I could just simply sum those. So you can see here, I've got the sum of all of the distances squared. Okay, then I'm going to divide by the number of values which I've got, but then right at the very end, I need to square root them. Does that make sense? Okay, so basically I go through, square all the distances, take the average of the squares of distances because they're all positive, and then I need to square root right at the very end. Okay, so this is all this notation is talking about. Now you notice here there's a difference. Just before I take the square root, I give that a name. Okay, so this formula down here is a standard deviation, which is what we've discussed. Okay, so standard deviation is just simply square of all the distances, add them all together, divide by the number of things which you've got, then square roots, the full thing, what I'm after. Standard deviation, average distance from the mean, remember? Whereas variance is what happens just before you take that square root. Okay, so this is really important. Okay, so the difference between variance and standard deviation. Okay, so variance is simply, well, you square all the distances, add them all together, and then divide by the number which you've got, and then that's fine, okay? Whereas the standard deviation is basically, okay, sum of all the distances, divide by the number which you've got, so that's my average, but then take the square root, okay? So you can say that the difference between variance and standard deviation, one is the square. So the variance is the square of standard deviation. So to show that, I'm going to use sigma to represent standard deviation. Okay, so sigma is the Greek letter for S, which is for spread. Okay, so the spread of the data is given by this, the average spread of the data, whereas the variance is just going to be the square of that. Okay, so this is really important. The difference between variance and standard deviation. Standard deviation is the average spread, whereas variance is the square of standard deviation. Now, my question is, why? Why does it make sense to give this a special name? Why does it make sense to give variance a special name? Because ultimately what we're interested in is the standard deviation. That's the average spread from the mean. So why does it make sense to give variance a special name, the bit just before we take the square root? Well, the answer is that variance will tell us and give us a good indicator of whether there's any outliers in our data. Okay, so let me show you this with an example. Let me just show you this with a very simple example. So here I've got my survival rates and my hospitals. So this is my hospitals. And these are my survival rates. In fact, no, I'm just going to do the distances. Okay, so I'm going to do the distances, which remember is the survival rates, take away the average survival rate. Okay, I'm just going to plot these on a graph. Okay, so let's suppose there's one value here. Let's say that value is at 2. Let's say there's one value here. Let's say that value is at 1. Let's say there's one value all the way out here. Let's say that value is up here at 10. Okay, so let's say that value up here is at 10. So let's just make my graph a little bit bigger. Cool, fantastic. Okay, so these are my distances. Okay, fine. So if I have a look at each of these, okay, and if I square them, we'll have a look. Well, that value there is 2, so when I square it, it'll become 4. Okay, that value there at the moment is 1 away from the average, which means that when I square it, it will remain 1. But have a look at this one over here. This value here is clearly an outlier. It's way outside the general trend of the data. And this value is 10 away from the average, so 10 away from mean, which means when I square it, it will become 100. Okay, so basically the reason why we have a different name for variance is a good indication of whether there's any outliers in the data. If there are outliers in the data, it means that they're going to be really far away from that average, really far away from the mean, which means that when I square it, i.e. the variance, okay, then it means that that variance is going to be really big. So if the variance is really big, it means that there's outliers in the data. Whereas the standard deviation, when we square root it again, we kind of lose that information. Okay, so basically the difference between variance and standard deviation, reason why we give variance a special name is because if there are outliers in the data, the variance is going to be massive. It's going to be exploded, all right? Whereas the standard deviation is just simply the average spread from the mean. Okay, so hopefully that kind of makes sense, all right? Okay, fine. So what I'm just going to do is just give you another version of the formula. Rather than calling it DI, just remember how I've calculated DI, how I've calculated those distances. I've taken the survival rate and taken away the average distance. So in other words, I take the value of each data point and I take away the average. Okay, so I can replace this formula here with the sum of xi minus x bar all squared and then take the average of them for variance. And obviously I just need to take the square root of that for the standard deviation. Okay, so kind of implicitly here then, I've been talking about population standard deviation or population variance. In other words, I've been dealing with the entire group. So these formulas here are talking about the entire group. Now this is really important actually, and it's worth mentioning here. The symbols that we give to measures of population. So if it's a population mean, remember you add all the values together and divide by the number which you've got, we give the Greek letter M for mean, okay, or median, or most, the average, and we call that mu, okay. Whereas if we're dealing with standard deviation, again we're dealing with spread, so we give it the Greek letter S for which is sigma there, okay. So if we're dealing with population, these formulas are true, okay. But here's my question: are the same formulas true if we're working with a sample? Well, let's have a look, okay. If we're working with jelly beans, let's say. Okay, so here's my population. You can think of the population is my complete jar of jelly beans, right? Whereas my sample would just be like a handful of them. So let's suppose I'm going to take 5 samples, and in each sample there's going to be 10 jelly beans. So in other words, I go into the jar and I take a handful out, and in the handful there are 10 jelly beans. Then I go again, take another handful out, 10 jelly beans, and I keep doing that 5 times. And in each handful there's going to be 10 jelly beans. So it'll be 5 handfuls of 10 jelly beans. Okay. So what I can do is calculate the mean weight of the sample and the standard deviation of the sample. Okay, so this is handful 1, and let's suppose the average weight of these 10 jelly beans was 18 grams with a standard deviation of 5 grams. Okay, and the same for sample 2. The average weight of these 10 jelly beans in handful 2 was 20 grams, and the standard deviation was 7 grams. Just remind me, standard deviation, measure average distance from the mean. Okay, so on average, my jelly beans, so the weight of each jelly bean was 5 grams away from the mean weight of 18 grams. Okay, and I've done that for all 5 handfuls. So basically for each of the 5 handfuls, I've calculated the mean of that handful, mean weight of that handful, and what the standard deviation was, what the average spread from the mean was. Okay, now if I'm going to plot this on a graph, okay, so let's suppose I knew that if I was going to take the entire jar of jelly beans, I could work out that the average weight of the entire jar of those jelly beans was 15 grams, and the standard deviation of the jelly beans should be 1 gram, okay? So basically, if I plot all of these on a graph, so on the left graph, I'm going to plot the weights of each of the samples, and on the right graph, I'm going to plot the standard deviations of each of the samples. So here we go. On the left graph, I basically plot the mean weight of each sample. So you can see here 18 grams, 20 grams, 15 grams, 14 grams, and 15 grams. And you can see they follow this kind of shape graph. Now, if you recognize this graph, if you recognize the shape of this graph, great. If you don't, we will meet it again in the normal distribution in theme 3. But effectively, you can see that there's a reasonable amount of weights clustered together, and then there's a few which are slightly more spread out towards the edges. Okay, so you can see that something like this basically happens, and the majority of the weights are something close to the 15 grams. Okay, so you can see that sample 3, for example, which had a weight of 15 grams, and sample 5, for example, which had a weight of 15 grams as well, that's close. Okay, so basically the left-hand graph, I'm just simply plotting the mean weight of each of these samples. Now, if I do the same for the standard deviations, I get something that looks like this. They're a little bit more spread out. Okay. Now again, there is still this kind of trend graph here, okay, but they're not quite closely clustered to where the true population standard deviation should be. So basically, the mean weights of the samples, they're better, they're closer to where the true population mean weight is, whereas the sample standard deviations are kind of further away from where the population standard deviation should be. Okay, so there's something interesting going on here, but I'm still not convinced. So what am I going to do? Well, I'm just going to do it again, but I'm just going to take more jelly beans in each of the samples. So instead of having 10 jelly beans in each handful, I'm going to have 20 jelly beans in each handful. And I'm still going to take 5 samples. So here we go. So let's suppose I get this data. Okay, so now let's see what happens. So I've got more jelly beans per sample. So going from 10 jelly beans in a handful to 20 jelly beans in a handful. Okay, let's now see what the data we get. So again, here's my data, and on the left graph, I'm going to put the mean weights. So okay, here are the mean weights. We've got 16, 15, 15, 15, 14. So here we go. I know that the true population mean weight should be here. And again, you kind of get this curve, but you notice that the curve is much more it's less spread out. Okay, it's much more peaked, if you like. And it's peaked close to where the true population mean weight should be. But if you look at the standard deviations, so here we go, I've plotted them here, well, they're certainly less spread out, but they're still not exactly the same as what the standard deviation of the population should be. In other words, the population is the true standard deviation of the entire jar, okay? So if I keep doing this then, this is what I should expect, okay? So with 10 jelly beans in each sample, okay, I get curves which are much more spread out, but they're still closely centered towards the mean. Okay, so for looking at the mean, the sample means are closely centered, and it just means that as I take more jelly beans, they become less spread out. Okay, so let me say that again in case you didn't catch it. Let's just look at the means first. If I take a smaller number of jelly beans in each handful, the sample mean weights should be more spread out. Okay, but they should still be closely centered to the true population mean weight. And all that happens, I can take more jelly beans in each sample, all that happens is that those mean weights become more centered around the true population mean weight. In other words, they become less spread out, okay, and you can see that. Whereas all that happens with the standard deviations, well, okay, if I take 10 jelly beans in each sample, in each handful, then it's really quite spread out, same as with the means, okay? But they're not closely centered to the true standard deviation weight, as true standard deviation, population standard deviation. Whereas what happens, I take more jelly beans, well, okay, they become more peaked, so they become less spread out, but they're still not centered around where the true standard deviation should be. So they're still a little bit off of where the true population standard deviation should be. Now this here is something called the central limit theorem, and we will meet this again, okay? We will meet this again. But basically, all I want you to take away for the moment is that for mean, so for the mean weight in this case, if you have fewer jelly beans in each handful, the mean weight should be more spread out, but they'll still be centered around the true population mean weight. Then all that happens as you take more jelly beans in each sample is that they will be less spread out. In other words, they'll be more peaked, but they'll still be centered around the true population mean weight. So you can see these two graphs here, they're still centered around the true population mean weight. Now, similar kind of thing with the standard deviations, they'll become less spread out as you take more jelly beans in each handful. However, they're still going to be a little bit off. Okay, so for the handfuls which have only got 10 jelly beans in, so fewer jelly beans, then they're really far away. The centre of the distribution is really far away from where it should be. And then as you take more jelly beans, it becomes closer to where it should be, but it's still a bit off. Okay, so fewer jelly beans, standard deviation is way off where it should be, whereas with more jelly beans, it's closer to where it should be, but it's not quite. Okay, so I'm always comparing it to what's happening at the population here. So the spread of the distribution decreases as you take more samples. Okay, the mean of the samples stays centered close to the true population mean. We've seen that. Okay, so they stay close to the true population mean. Whereas the sample standard deviation gets closer to the true population mean, so it's closer to the true population standard deviation. However, it will still be a little bit off. Okay, so standard deviation of the samples gets closer to where it should be, but it's still going to be a little bit off. Okay, so here's what I want to do. Here's how I find the mean. Okay, of the population. Here's how I find the mean of the sample. Now you notice the difference between the notation. This is really important. Okay, so for a mean, the population notation is with the Greek letter m, mu. Whereas for a sample, we tend to just say that's x bar. So the mean of a sample is just x bar. Okay. If you're dealing with standard deviation, the population notation is the Greek letter s or sigma. Whereas for the standard deviation for a sample is the English letter S. All right. So what we need to do is we need to incorporate this idea of here. So we need to say that for the mean, it doesn't matter. Okay. For the mean, as you take more samples, it just becomes less spread out. But actually, the mean, the sample means will become closer to the true population mean. Whereas for standard deviation, okay, it becomes less spread out, but actually the standard deviation of the samples will still be a little bit off of the true population standard deviation. Okay, so what I can do is use Bessel's correction, otherwise known as degrees of freedom, to approximate this, to represent the idea that the sample standard deviation will still be a little bit off of where the population standard deviation actually is, but it gets closer to the population standard deviation over time. Okay, so as the samples increase. So basically with small samples, the standard deviation of the sample is off by a lot. So if you have a small number of samples, the standard deviation is off by a lot. Whereas with big samples, in other words, more things in each sample, the standard deviation is off by just a little bit of the true population. So remember, this is all to do with this idea which I was talking about in the last theme, which is that the whole point of statistics is making inferences. It's understanding what's happening at the sample level to infer what's happening at the population level. That's literally what we're doing right now. Okay, we're basically saying, well, okay, with standard deviation, we know that at the sample level, it will be off of the true population standard deviation by a bit. And the amount that it's off by depends on the size of the sample. So if it's a small sample, standard deviation is off by a lot. If it's a big sample, the standard deviation is off by a little bit. So let me just consider this, just a little thought experiment. If I take, for example, 5 over 5, or 10 over 10, or 100 over 100, these are all equal to 1. They're all equal to the same value, right? Let me just show you what happens then to take this idea into account. So basically I want that with small samples, remember the sample bit is on the denominator. Okay, the way which we calculate sample mean, or sample standard deviation, is on the denominator. Okay, so they divide by n bit, right? So if I want to say that the samples standard deviation is off by a lot, and if the big samples, the standard deviation is off by a little bit, I can just basically say that if you've got a sample, just use n minus 1 instead of n. So you can see for this formula here, you've got n on the denominator. Whereas with this formula here, you've got n minus 1 on the denominator. Okay, and I can illustrate this with this idea. If I change 5 over 5 to be 5 over 4, so in other words, I change this denominator to be 1 less, okay, or if I change 10 to be 9, or 100 to be 99, so I'm just basically taking 1 away from each of the denominators. In other words, I'm making n become n minus 1, okay. Watch what happens. Well, no longer are these values worth 1 anymore, so 5 over 4 is 1.25, so it's gone from 1 to 1.25. Well, that's an increase of 25%. If you look at the next one, it's gone from 1 to 1.11. That's an increase of 11%. If you look at the next one, it's gone from 1 to 1.01. That's an increase of 1%. Okay, so basically what I'm saying here, this is exactly what I want. If I have a small number of samples, in other words, that denominator is small, okay, because remember, the number of samples always goes on the denominator of these formulas, okay? Well, if I've got a sample, remember, with a small number of samples, the standard deviation will be off by a lot. Well, that's a lot, okay? I start with five samples, okay? And if I decrease the denominator by 1, then it basically is increased by a lot, okay? It's off by a lot. Whereas if I start with a big sample, like 100 samples, if I take n minus 1 on the denominator, then it's only off by a little bit. It's only off by 1%. That's exactly what I want, okay? So if you've ever wondered why this formula has n on the denominator if it's a population, but n minus 1 on the denominator if it's a sample, this is the reason. It's a degrees of freedom, or a Bessel's correction, okay? It's this idea that for small samples, the standard deviation will be off by a little bit from the true population standard deviation. Whereas with big samples, the standard deviation will only be off by a little bit, okay? Whereas you notice for mean, we don't need to do this n minus 1 correction. So it's only for standard deviation. The n becomes n minus 1 if you're dealing with a sample. Whereas for mean, you don't need to worry about that. Reason being is because actually, as the number of samples increase, the mean will remain centered around where it should be. Okay, so hopefully that makes sense. Now, here's my next question. Is there an alternative formula for variance? So this was the formula for variance that we've got at the moment, okay? So this formula for variance here. So I'm using variance because it's a little bit easier to work with, but just remember, to get standard deviation, you just need to take the square root anyway, okay? So you notice I'm just going to use the population formula. So xi minus x bar squared, add it all together, divide by n. That's the formula for variance, right? So I've written that out again here. Is there another formula for variance which requires less computation? Because the thing is, this is quite computationally expensive. Basically what you've got to do is take the actual value of the data point, so in this case the hospital survival rate, and take away the mean survival rate for every single hospital. Then I've got to square all of those individual distances. Then I've got to add the squares of those distances together. Then I've got to divide by n. That's quite computationally expensive, and perhaps is there slightly an easier formula which you can use? Well, yes, there is. And I'm going to talk you through this now. So first things first, what I'm going to do is I'm going to take this xi minus x bar all squared. I'm just simply going to expand the brackets. Okay, so just a simple quadratic, xi minus x bar all squared, I expand the brackets, I get this. Okay. Now, if I distribute the summation, so I'm going to take the sum of 1 over n, and I'm going to put it through every single thing on inside the brackets. So I get the sum of 1 over n of xi squared, so that's the first term. Then there's 1 over n times the sum of, and then negative 2 times by xi times by x bar, and then finally the 1 over n of x bar all squared. And that's the third formula. You notice here, I've just decided to pull the 2 out the front of the summation. The reason being is because the sum of 2 times something, the 2 of something, is the same as 2 times the sum of something, okay? So I can just pull that 2 out. Okay, now just remember, x bar is just a number, okay? So x bar is just a value, it's just an average, which means that, again, I could just pull that out. So again, that number times by xi is the same as the x bar times the sum of that value, okay? And if you have a look at the last one as well, if I'm basically adding together lots of x bar squareds, well, how many x bar squareds am I adding together? I'm adding n of them. So I do 1 x bar squared, then I add on another x bar squared, then I add another x bar squared, etc, 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 right the way through to however many I've got, right the way up to n. Then I get n times by x bar squared. Well, are you happy now I can make a little bit of a simplification? For example, the 1 over n times the n, they just cancel. So I'm just left with x bar squared here. And I'm just going to basically take the 1 over n and put it over the sum of x over n, okay? Now you notice that this thing here now is just simply the mean, okay? If I add the values together and divide by n, I just simply get the mean. So you can see here I've changed this to the mean. And the first term I haven't changed at all. Now, if I have a look at this then, well look, x bar times x bar, that's just the same as x bar squared. And notice that I can combine these together as well. So I get minus 2 x bar squared plus x bar squared. So, okay, negative 2x bar squared plus x bar squared is negative x bar squared. So I get this formula here. Now, just to make it a little bit easier, I guess, what I could do is actually just pull out an n from this thing. Okay, so I've just basically just done a little bit of expanding, and I've shown that the original formula which I had for variance can also be this. Well, if you have a look, I know that there's just a 1 there, but because I see a 1 over n here as well, I'm just being a bit sneaky and being like, well, actually, I don't really like the 1 over n sitting there on its own. So what I'm going to do is basically just write that 1 in front of the x bar squared and just write it as n over n, okay? So if I factorise a 1 over n from each term, then I can factorise a 1 over n from here, and I basically just get this. So it's just one nice big bracket there, All right. So another way of writing the formula for variance, I could stick with the original one, which is more closely related to the difference from the average. Okay. But actually, this is another version which I could use as well. Okay. So just something to be aware of. So just finally, then, in summary, what have we got? Well, measures of spread tells us the variability in the data. Okay, so measures of spread, sometimes called measures of variability, tells us how much the data is varying. It's a measure of how much variation there is in the data. So in general, if there's a high measure of spread, it means that there's more variability in the data. The data points are more spread out. Whereas if there's a low measure of spread, it means that there's less variability in the data. Okay, the data points are quite closely clustered together. Now, the most commonly used measures of spread are range. There's also quartiles and deciles and percentiles on there. I haven't bothered to put them on here, but there are also those as well to bear in mind. But then variance and standard deviation. Now, just remember the difference between variance and standard deviation. I wonder if you can tell me. Okay, variance is basically what happens before you take the square root bit of the standard deviation calculation. So standard deviation is where you want to end up at. Okay, that will tell you the average distance from the mean. Okay, so standard deviation is what you want. It's the average distance of each data point from the mean, okay, in your data set. But the variance is what happens just before you take that square root. In other words, it's the square of standard deviation. And what that will tell you is it's an indicator of whether there are outliers in the data or not. Okay, so if the variance is really big, it's because there are outliers in the data. Okay, just remember when we did this example here, okay, so if I had the distances plotted here, so this first distance was 2, second distance was 1, and this last distance was 10, okay, well, okay, when I square it, the 2 still remains relatively small, the 1 still remains relatively small, but the 10 just explodes, just gets massive, because I'm squaring, okay, so if there's outliers in your data set, the variance is much better at picking those up. Also, the reason why we sometimes use variance is because it's not always necessary to find the standard deviation. Sometimes with calculations, so when we look at theme 3, we'll look at this idea of expectation algebra. Sometimes it's just easier to work with variance, and that's enough. That's enough to get an idea of what's happening here before we take the square root. Okay, so hopefully that gives you a bit of an idea. Now, what do I want you to do for homework as part of the self-study task? Well, basically, I'm going to give you a set of questions, and I just simply want to find the standard deviation of this data. Okay, so here we go. Here's the question which I'm going to give you. I'm going to give you the data set, this data set here. Let's find it. So it's going to be this one here. So let me just get rid of that, get rid of that, get rid of that. So here we go. Here's the data set which I want you to use. And I'll copy it down here. So here's the data set which I want you to use, and all I want you to do is to find, well, first of all, the variance of this data set, and then secondly, the standard deviation. Now you can assume that this here is a sample. Okay, so let's suppose this is a sample of a bigger data set, sample of a population, and I want you to find the variance and the standard deviation of this data set for me. Okay, and can you upload that to Flipgrid by next Monday at 5 p.m. Thank you.